All right, I think we can get started. And just so you know, Professor Emanuel, there are over 70 attendees here, and I expect more people will be coming. Okay, so hello, everyone. Welcome to ethics seminar series. This is John, the seminar coordinator, and together with me is Miss Kathy Medley. Kathy is our communication specialist, and Kathy and I will be the moderator today. Today, we are thrilled to have our speaker, Professor Kerry Emanuel, joining us from MIT. Okay, so just a few things before we started. The seminar is being recorded, and the video will be put on our YouTube channel later. Please feel free to ask questions through chat, or you can raise your virtual hands, and Kathy will unmute you. So Dr. Kerry Emanuel is a renowned atmospheric scientist. He needs no introduction, but still I will read his bio. So Dr. Kerry Emanuel is Cecil and Ida Green Professor of Atmospheric Science at MIT. He has been on the faculty at MIT since 1981, after spending 3 years on the faculty of UCLA. His initial focus was on the dynamics of rain and snow bending in winter storms, but his interest gradually migrated to the meteorology of the tropics and to climate change. His specialty is hurricane physics, and he was the first to investigate how long-time climate change could affect hurricane activity, an issue that continues to occupy him today. His interests also include cumulus convection and advanced methods of sampling the atmosphere in aid of numerical weather prediction. He is the author and co-author of over 200 peer-reviewed papers and 3 books, including Divine Wind, The History and Science of Hurricanes, published by Oxford University Press and aimed at a general audience, and another book, What We Know About Climate Change, published by the MIT Press, and now entering its 3rd edition. He is a co-director of MIT's Lawrence Center, a climate think tank devoted to basic curiosity-driven climate research. He is a member of the National Academy of Science, American Academy of Arts and Science, American Philosophical Society, and a founding member of the Royal Society. Now let's welcome the speaker, and I'm going to give the ball to Dr. Emanuel. Dr. Emanuel, please proceed.
Well, thank you very much, John, and it's nice to be with all of you this afternoon. I wish I could be with you really, but we're all making do these days. And today what I want to do is to talk to you about what I consider to be a really important problem that's on the interface of weather and climate, which is how you go about estimating weather risks and how they might be evolving with climate. So my seminar is directed toward using physics to do this. And let me try to explain why I think this is important. If you start digging around to find out how our society long-term risks, I don't mean response forecasts. For example, how much wind insurance are you paying on your house if you own a house, and how much flood insurance? What's determining those numbers? I think you might be a little bit surprised by that. It comes out of a whole industry called the risk modeling industry. And I would argue that this industry is sort of stuck in the past, and we're basing our risks on history, which is no longer valid. So almost all current risk assessments, professional risk assessments, are based on historical statistics. That would be fine if those statistics, if they were long. they're any good. But that isn't. The historical records are flawed. They're short, particularly outside North America. And as I hinted, the past 50 to 150 years, which is usually the basis for a lot of these risk assessments, is already a poor guide to the present. It's because of climate change that has already happened. So this whole business that risk and insurance rates and so forth don't need to worry about climate change because, well, they're writing one-year contracts and 30 years away or something. It's false because their current estimate of their current risk in many cases is already badly outdated, and I'm going to try to illustrate that. The risk modelers have been slow to migrate to a physics-based approach, and I'm strongly advocating that they do that. So let's talk about this, and I want to just talk about the natural disaster problem in general before we kind of narrow things down to floods. And it's sort of an anthropological observation that societies are usually pretty well adapted to frequent events. It's no big surprise if they happen all the time. Buildings and infrastructure and human beings themselves are pretty well adapted to them. And it turns out frequent means, in very loose terms, more than about once per 100 years. What's magic about 100 years? A few human generations. But conversely, they're often poorly adapted to rare events. Okay, less than about once in 100 years. And there you get large increases in damage when things that used to be less frequent than once in 100 years become more frequent than that. So this is kind of a generic curve showing the percent of property destroyed versus the return period of the phenomenon that's doing the destruction. And this is an almost universal curve. It doesn't matter whether you're talking about earthquakes or hurricanes or fires, big fires. You could see that these frequent events, once every few decades, they don't do anything because we're adapted to them. If you get a really infrequent event, it's going to destroy everything 100%. The steep part of the curve happens to be around 100 years. So if you take an event that was a 120-year event and it becomes an 80-year event, you're really going to see very large increases in destruction. And it's simply because society is well adapted to the remarkably stable climate we've enjoyed since roughly the end of the last ice age. So I'm going to use a particular example of tropical cyclone wind risk just to illustrate the point, and then we're going to get to floods soon. So I'm not going to tell you now where these curves came from. I just want to focus on what they mean. So here we have probability density, right? Probability per unit log of damage. This is damage, and what we see is wind damage to somebody's portfolio of insured property in the eastern United States. These are all over the eastern United States. All of them, or most of them, are susceptible to hurricanes. And the blue curve is a curve that's for the climate on the average of 1984 to 2014. You notice that the most probable loss is about $1 million to this particular portfolio. This is not the whole country by any means, it's just a portfolio of property. The red is for the climate at the end of this century, assuming that we don't do very much to curb fossil fuel combustion. So there's a little bit of a shift. It becomes less probable to see these relatively low damage events and more probable to get the high damage events. A little bit of a shift here, okay? And the most probable damage goes from maybe just under 1 million to just more than 1 million. And say, well, okay. And now I'm going to show you exactly the same data, but I'm going to multiply the probability density by the damage. So it's the same data, but displayed a different way. Now this time, the area under these curves is proportional to the long-term expected damage. You want to wait a long time. This is the amount of damage you would see in the climate of the late 20th century, and this is the amount of damage you'd see in the climate of the late 21st century. More than 3 times as much damage, okay? But notice that this is coming, right? It's way out here at the tail of what the other probability distribution is. Let's go back. The most probable storm was $1 million. But that most probable storm hardly contributes to the long-term damage. Okay, your average run-of-the-mill hurricane doesn't even count when you're adding up long-term damage. It's the tail events, okay, that do the damage. Now, some of you probably already know that, but it's very stark. And although I'm illustrating this for hurricane winds, it's really true of a wide variety of phenomena, because it's the rare events that get people, that they're not prepared for, that society is not adapted to, all right? So, okay, now with that in mind, let's look at where in the United States, which weather phenomena get us, okay? This is from NOAA, Center for Environmental Prediction. This is US damage over 1980 to 2020. That's been adjusted by the Consumer Price Index for the year in question. And then this is the phenomenon: tropical storm, severe storm, drought, flood, wildfire, winter storm, freeze. Now, there's some ambiguity. I don't even know, in this category flood, is this just the big riverine floods like Mississippi River floods, or does it also include floods from tropical cyclones? I suspect not. I suspect tropical cyclone floods are put under tropical storms, but I don't know that for sure. You can see that the tropical storms and severe storms, these are thunderstorms mostly, drought and flood are our big problems. Wildfires, as we all know, also can cause big problems. Now let's look at this over time. This again is CPI adjusted. This is this is summing over all these phenomena, by the way, 1980s, 90s, 2000s, 2010s, and this is just 2017 to 19. And you can see this big rise. Now, some of this is demographic. It's simply because a lot of people are moving to risky places like the coast, the tropical, subtropical coastlines and so forth. But it's not clear that all of it can be explained by demographics. All right, so what's wrong with just using historical records to assess long-term weather risk? Well, with riverine floods in the US, Mississippi River, though, we have, depending on where you are, roughly 100 years of good records. The short-term floods, the flash floods, the TC-induced floods, not so good, probably a little bit less than 100 years of usable records. But even if we had 100 years of records, first of all, 100 years, you need a lot more than 100 years to get the 100-year event in a particular place. And we don't have that. And it's the rare events we're concerned about. But the big problem is the past is no longer a good guide to the present. Now, remember, I'm using the word present here, not future. It's also not a good guide to the future. But the salient point here is it's not even a good guide to the present. And I'll get back to that as an example. So we really need to get away from the 100% reliance on historical records to estimate long-term risks. It's the most important thing I have to say today. And if you already believe it, you don't have to stick around, but I want to try to put some flesh on those bones. Okay, and I'm going to now focus on hurricane flood risk because I've been working on that, and that's also, I think, a pretty important contributor to flood risk in general, but I'm not going to be talking now specifically about riverine long-term floods, but we can talk about that in the questions if you like. So globally, on average, there are about 15,000 deaths per year. That's been true since 1971. $1.1 trillion 2015 in damages accumulated globally since 1971, about 21 billion a year. So it's a pretty big number. And this is the worrying thing, is the global population that's exposed to hurricane hazards has tripled since 1970. So part of this is just general population growth, but most of it is migration to hurricane-prone places. And correspondingly, we see big increases in global tropical cyclone damage. And this is damage normalized by the gross world product, okay? So it's been normalized that way. And since 1970, we've had a 380% increase on average in tropical cyclone damage. The population in TC-prone regions, as I've just said, is increased by about 200%. So that suggests that maybe climate change has played some role in this, but in any case, we can agree it's going up. So what are the hurricane risks? Well, we talked about wind, and that's what most people think of when you mention hurricane. But a lot of the damage is really water damage, heavy floods from torrential rains, and of course, a storm surge, which is also one of the most lethal aspects of the storms. If you look at mortality in the United States, 1970 to 1999, from tropical cyclones, from hurricanes, this just shows the source of that mortality. It's almost all water, either fresh water from rain, salt water from the surge. And wind is pretty pale by comparison to those two put together. So it's all about water, although the wind is the only thing that's in this chart that's privately insured. Well, tornadoes are wind as well in that sense. And that makes a difference in perception and makes a difference in how society responds and so forth. But that's a social science issue I won't go into here. Is this risk? Yes, it was predicted to change, and we have pretty solid observational evidence now that it is. So this is a chart that was just published this last summer by Jim Cosson at the University of Wisconsin and his colleagues in PNAS. It shows from 1980 to 1979 to 2017 the proportion of satellite-derived hurricane fixes that were categorized as major, that is Cat 3 and above storms. And you can see a big increase in that fraction, which is, again, in accord with what theory had predicted dating back 30 years ago, that we ought to be seeing trends like this. There's a lot that goes into this analysis, including having to compensate for the poor quality of the earlier satellite images, but this is a pretty solid result. Also from Jim Cosson and colleagues, this is showing that the latitude, or the distance from the equator, at which storms reach their peak intensity has been steadily migrating poleward. So toward higher latitudes in both the northern hemisphere at the top and the southern hemisphere at the bottom, from best track data, also from satellite data. So hurricanes are reaching their peaks further poleward, and they're becoming more intense. The thermodynamic bound, called the potential intensity, which you can calculate easily from climate data. It's just really a function of the temperature of the atmosphere of the ocean, not much more than that. This is showing the linear trend in potential intensity in meters per second per century from ERA5 reanalysis over this period, 1979 to 2018, and I'm only showing you where it's statistically significant at some level. And you can see in most places, most of the hurricane regions, the potential intensity is going up. This is the same kind of chart, but from a climate model run into later this century, again showing the trend from the climate model. This is a GFDL NOAA climate model. And you can see that the trends are positive in the cyclone region, especially in their peripheries, the subtropics, here, which is consistent with the fact that we're observing a poleward trend in the latitude at which storms reach their peak intensity. So potential intensity, we knew from basic theory, increases with global warming. Incidence of high intensity hurricanes should increase. It is, apparently. And it should be faster in the subtropics, and that seems to be I didn't tell you why that's true theoretically. That's an interesting story, but it is. And the other thing that comes from very simple theory, basically the Clausius-Clapeyron equation, is a given hurricane should produce substantially more rain. And this turns out to be, in my view, the big deal, much bigger deal than the wind. All right, so if we're not going to use history, we're going to use models. We're going to use physical models to estimate hurricane flood risk. So how do we go about doing this? Oh, I like this slide because it shows this example of climate change adaptation with these little sticks to hold up the palm trees. I think that's as much as the current government of Florida will allow anybody to do by way of adaptation, but there you have it. So why not just use climate models to simulate future hurricanes? After all, they're simulating future climate, and they do have storms in them that people call hurricanes, but they're really badly under-resolved. And so I would say you can't use them yet. There are others who would disagree, but let me try to show you what I mean by that. So all I'm showing you here is a histogram of hurricanes. This happens to be for the Eastern North Pacific, by their lifetime peak wind speed in meters per second. And that black vertical line is the distinction between category 2 and category 3. So the black is observed. Most storms are weak, but there are a certain number of destructive storms at these high categories. But the modeled storm, and this is a pretty state-of-the-art, it's actually a 50-kilometer global model, doesn't get too much better than that, doesn't about meters per second. People are getting better at this, but numerical convergence experiments show rather definitively you have to have grid spacing down in the kilometer range before you can claim to be numerically converged on storms like this. So I mean, it's like trying to simulate baroclinic cyclones, the model with 1,000-kilometer grid spacing. You get something, but global models just don't simulate the storms that we're really interested in, I would argue. So we have to do something else. And what we do at MIT is we begin with a climate model or climate reanalysis or scale climate. The climate analyses are fairly robust. They're widely available. And we cull from these climate reanalyses or models the key statistics that are known to influence tropical cyclones. We bootstrap these into unlimited, at least potentially unlimited, synthetic time series of hurricane-relevant environmental variables, potential intensity, wind shear, humidity, and so forth. And we use those to draw very special that have been used, for example, in actual real-time forecasting. I'm using something called the CHIPS model. And it's a very, very long story, which I don't have time to tell, and it's kind of an old story. We've been doing this for 15 years. Whatever the technique, you're not going to really believe it unless you can extensively evaluate it against historical hurricane data. That's where history is, in fact, very valuable and necessary for this exercise. Once you've done it for a climate reanalysis, it's fairly trivial to apply that to the output of climate models. So it's a downscaling technique. Well, here's an example of that. This is 100 of a set of 6,200 tropical cyclones in the North Atlantic. We do this globally, or can do it globally, by the way, but this is for the North Atlantic. Downscale from NCEP reanalysis. And the blue dots are where the storms nominally reach 35 knots peak intensity. And the colors have something to do with the peak wind speeds along the tracks, but you can follow these tracks. This happens to be for U.S. landfalling storms. And the storms in this set, see, we can what it is we're interested in. And the nice thing about this set is that, unlike the GCMs themselves, it captures the entire intensity distribution. So this is an exceedance frequency of lifetime maximum intensity. This happens to be for a set of Atlantic storms. The blue is from historical hurricane data, so-called best track data. The red is from the synthetic technique, and the green bars are estimates of sampling error, just from the low sample size of the historical tracks. And you can see that you get the whole intensity distribution this way. It does a very good job with a seasonal cycle, number of storms in each of the 12 months of the year in the Atlantic, averaged over 1980 to 2012. The blue dots are from historical data. The red is from a much larger set of synthetic tracks, and the blue shading is, again, an estimate of sampling error. Climate phenomena like ENSO and the Atlantic meridional mode. This is just 3 phases of ENSO and 2 phases of the AMM, comparing, this is for the North Atlantic again, the historical data in blue into the synthetic data in red. So it does a very good job capturing the known suppression of North Atlantic storms by El Nino, for example. And this is just the time series of a hurricane metric called power dissipation from observations in blue going back to 1980 or so, and from the synthetic method in red. These have been downscaled from NCEP reanalysis. Curiously, if you downscale ERA5, you get a somewhat lower correlation, still significant. But my experience, this downscaling technique in the Atlantic works much better with NCEP reanalysis than with ERA. The beauty of this is you can generate an arbitrarily large number of events with this technique. It's computationally very, very fast. And so if you're interested, for example, in the wind speeds of landfalling New England hurricane, you can try data. I'm going all the way back to 1900. Those are the green dots. So this is return period on a log scale. This is wind speed. And you can go out to, maybe return period of a few tens of years with that historical data. But with the synthetic data, the blue dots, you can go, well, this one just goes 100 years, but you can go further if you want to. Don't worry about extreme value curve fit to that distribution. All right, so we've been talking just for the last few minutes about hurricane winds, and commercial risk modeling has focused almost entirely on wind because the feds insure water. That's basically the heart of it. But in fact, most damage and mortality is caused by water. And so we've got to do something about that. Well, on the saltwater side, once you have the synthetic wind events, which includes the whole time evolving surface wind field, among other things, you can use that to drive a hydrodynamic surge model. And I'm showing you here for a study we did more than, just about 10 years ago for the city of New York, pre-Sandy, by the way, grids of 2 models. The slosh is a publicly available NOAA surge model. We just happen to use this circular grid. And then the dots you see in the background are for a more sophisticated, expensive model, ADCIRC, which is on a non-standard grid like that. So we use those kinds of models to and drove them with the hurricane wind fields and got curves like this. This is from a paper we published in 2010, showing the expected return period of surge at the Battery, the southern tip of Manhattan, where there's a tide gauge. The storm surge is in green. If you add on high tide, you get black, and there's some range of uncertainty. This again is from a set of synthetic tracks driving a surge model. 2 years later, we had Sandy. We would have estimated that Sandy was about a 400-year event in the climate of the late 20th century. This is using climate data. Synthetic tracks is using climate data from the late 20th century. That's the sort of thing you can do. But now rain is an interesting problem, okay? And it's an interesting technical problem. It's a heavy rain can be coupled to a stream flow model or an urban flooding model to predict flooding. I'm just going to talk about the rain part of it today for lack of time, but you have to start with the rain. And there's an interesting technical model. The models that we use actually predict updraft and downdraft mass fluxes. We know what the environmental temperature is. But the rain fields are strongly two-dimensional. I mean, they're not axisymmetric at all, strongly influenced by topography and so forth. Just storing those variables would totally swamp if you're talking about 10,000 or in some cases 100,000 events that we generate, and you want to unpack those into a full time evolving two-dimensional field, you've got a big storage problem, okay? So we don't do that. What we do is use physics again. In this case, quasi-balanced dynamics. Some of you have been, I'm sure, know about that. And what we do is unpack the fields that we do store into time-evolving two-dimensional wind. It's not axisymmetric because we're adding components that have to do with the background wind. And then we're using that, and it's a bit of a story. We're unpacking that into a vertical velocity field by using quasi-balanced dynamics, things you learn in graduate school in atmospheric dynamics. And that's strongly influenced by topography, shear, variations in drag coefficient, the whole works. It's a long story. In Monica Feldman from Switzerland and I worked on this, and it was published in Journal of Applied Meteorology and Climatology in 2019, if you want to look at the details. And so it works pretty well. This is just showing you the contours of storm total rainfall from a Gulf of Mexico storm. This is the northwestern Gulf. Texas is over here. Whose center passed along this line. These dots are evenly spaced. I can't remember how many hours now. And this is a particularly intense rainfall, peaks of around 18 inches storm total rainfall for this track. And this is downscaled from, in this case, ERA5 reanalysis. This is a September 1980 synthetic storm, all right? And you see all kinds of influences from varying drag coefficients, and it's clearly not going to be an axisymmetric rain field. Sorry, I'm going backwards. But when you have 100,000 events, you can calculate the 2,000-year event. Well, here's a 2,000-year event, okay? You're not going to see that in the observations. This storm, same part of the world, came up toward Houston, took a look at it, thought better, and went out to sea and produced 50 inches of rain in this region, okay? Now, you might think that's impossible. It isn't, okay? We've had rainfall in the meters in places like Taiwan, recorded from a single store, Réunion Island, but this is a very rare event for the current climate anyway in Texas. That's why that's one of the things that applying physics, as long as you're confident that you can do it. So where does that confidence come from? Well, it comes from, this is the hard part. With wind, it's hard enough. With rain, it's almost impossible. With Monica Feldman, we sort of figured out how to do it. So the way we tested the algorithm was to identify rainfall that was somewhere near NEXRAD sites around the US, and I'll show you a map of those. And we found rain gauges from this daily global climatology that were relatively near the NEXRAD sites, and we chose networks of rain gauges. So we had two kinds of data, radar data and rain gauge data. They both have limitations, of course. And so we were able, through a large downscaled events in the current recent climate, to compare the statistical distributions we get from the synthetic data and also from the. So here's the network of, here's the network of NEXRAD sites that we actually use exercise. And here is the result. So what we're looking at is storm total rainfall on this axis and the annual frequency of occurrence. Okay, this is just a different way of it. So this is highly frequent on the right, this is rare on the left, and this is the amount. The gray dots have been derived from a large set of our MIT synthetic tracks. The blue dots come from the rain gauges, and the red dots from the NEXRAD radars, all right? And then the shading is our estimate of sampling error from those two different sources. This is just Jacksonville, Florida, but we did it for all the sites that you saw on that map. And if you want to see the rest of the sites, have a look at this. It's not too bad, actually. We're quite happy with the way this turned out. All right, so having established a technique for getting rain, we can now also apply that to the effects of climate change. What are those qualitatively? Well, the big deal is there's more moisture in the boundary layer because it's warmer. It's very simple physics. The storms tend to be stronger. That's not universally the case. There are places where they get weaker, but mostly they get stronger. On the other hand, their cores tend to be more compact, and that weighs in the other direction. The storm, the heavy rain region passes quicker, but it's raining harder. We don't know very much about how climate change affects storm diameters, but what little we do have theoretically in the model suggests they might get a bit larger. That's kind of dicey. And storm, depending on where you are, storms might be moving faster or slower. There isn't anything universal about this. There's a lot of statements floating around the media or so. There may be places where it speeds up. There may be other places where it slows down. All climate change in the end is local. So we take this technique and we can apply it to CMIP6 models, for example. We just published, or just publishing a paper where we did this globally. This is for wind from 9 current generation CMIP6 climate models. The blue is for the 20th century. Now this we decided to do because these fields were ready. Basically, it's just 1% per year CO2, that's all. And the shading, so this is the frequency of category 5 storms on the planet, around the planet. The shading is the scatter among these 9 models for the 20th century. And then we arbitrarily started the CO2, I think it was in 1970 or something like that. And you can see that you get more Cat 5 storms. Kind of an aside. Well, let's look at what it does to rainfall. So I thought the way I would first display this, because it's, you can't display the storm maximum rainfall. It doesn't mean anything. Storm that interacts with mountains produces a whole lot more rain than a storm that doesn't, for example. So I've created a set of landfalling, U.S. landfalling tropical cyclones, and looked at the rainfall at the geometric centroid of each county in the eastern U.S. Now, that doesn't mean too much because, of course, if you go to the coast, there's going to be more rain. If there's a mountain somewhere, any color for these climate models run during this period. And you can see the most rainfall, it doesn't surprise you, is along the Gulf Coast and Florida. Okay. Now we're going to look at the experiment called 3.7.0, sort of the middle of the road warming experiment at the end of this century, same color scale, all right? If you compare the two, same color scale, you can see these huge increases in rain, really big increases, mostly in the places that are already susceptible to hurricane rain. You can see the mountain effect here in the Appalachians, all right? This is what worries me and why I'm giving this seminar. The winds, I could show you the winds, they increase too, and that's worrisome, but this to me is much more worrying, that together with the storm surge. Let's look at a particular place as a matter of illustration. I've done this for Houston, partly because Houston's had so many problems lately. But this is from this collection of 9 models, and what you're looking at is the storm rainfall. I put this in inches here. In this case, this is the return period on a log scale. And this is for the late 20th century in blue, 1981 to 2000. It's for the model average frequency converted to a return period. The shading shows the scatter among the downscaled models. And the red is for 2081 to 2100 under this moderate warming scenario. And to give you a feeling for this, 30 inches, which is sort of on the order of a Harvey, is a little bit more. Harvey was a little bit more than that, not much more. A 2,000-year event in 1990, and it becomes a 140-year event in. All right, that's huge. because we're looking out at the high rainfall tail. So 15-fold increase the probability of this kind of rain in Harris County by the century's end. But here's the point, and I didn't put the curve on the map. Already, it's a factor of 3 larger, already. And not very long ago, 3 separate papers by 3 completely independent research groups came to the conclusion that the probability of Harvey had increased by order 2 or 3 since the late 20th century. So I'm not the only one coming to this conclusion. Now, if your insurance and your infrastructure and your whole policy is based on what the risk modelers are giving you, it's wrong, okay? By a factor of 3. It could be wrong by a factor of 3. It's no good, all right? That's why we have to move away from historical statistics. Here's a future end of century 100-year rain event for Houston. Look at the contours here, all right? 50 inches in peak rainfall. Now in Houston itself, it's more like 50 inches. What would happen if that actually happened? That's a 100-year event. I mean, it's very rare, even by the end of the century, but not that rare, okay? That could happen. What would that do to the infrastructure of Houston? Well, if you start looking at other parts of the world, your eyes really begin to pop. Here is a typhoon that came up and stalled just to the west of Taiwan. Taiwan is under these rain contours here. 7 meters of rain, all right? Well, you're probably thinking that's impossible. It is impossible in the current climate, but it won't be impossible then if these climate models are anything like right. Now, Taiwan has had, in the historical period, 2.5 meters of rain from a typhoon, quite recently, actually. But what happens when you have 7 meters of rain? What's that going to do? And of course, we have the storm surge problem as well. This is a wind-related, but still it's a water phenomenon. This is an older study, again, going back to, it was published before Sandy. And it's for the Battery in New York, 4 different climate models of an earlier generation. The black curve shows the 20th century estimate. The red and blue curves show estimates toward the end of the century, but including a meter of projected sea level rise. So in all cases, you have all 4 models project rather substantial increases in saltwater flooding risk. Now, there are places in the world, including MIT campus, where I live, where you have a river that's not far from emptying into the sea, have a storm surge and pulses of fresh water coming down the river at the same time. I wonder what would happen if you tried to model, which we're trying to do now, by the way, of this kind of thing. So let me go to my takeaway points. The main thing, as I've said before, is we've got to move away from the sole dependence on flawed historical data and assessing climate and weather-related natural hazard risk, and embrace advanced modeling techniques. The modelers really need to pay more attention to the fact that in the end, a lot of the climate change is felt through weather, and we better try to be modeling the weather accurately and not just things like global climate. The other point, which is terribly important for planning and for adaptation and so forth, is that we cannot any longer regard climate change as a problem. Sure. Okay. So insurance companies, much to their credit, have started to really understand this message. Only a few years ago, the standard line you got from them was, well, we're writing 1-year contracts. Who cares about 30 years from now? Now they get the message that their existing risk estimates can be way off the mark because of climate change that's already happened. And finally, industries and maybe other organizations, governments, could help catalyze industry-relevant research in things like natural hazard risk in universities and in government labs by creating a demand for students, graduates, with backgrounds in physics-based risk assessment. We're not doing a very good job right now turning out these students. We're turning out students with excellent physics and modeling capabilities, but they are being employed for the usual purposes, which are perfectly, absolutely necessary, like weather forecasting or climate projections, not so much for this kind of risk assessment. And I'll leave you with those points. And John, I'm happy to take any questions if you want to involve me.
If anyone has any questions, they can raise the virtual hand. There should be a little button right below the attendees tab, or they can send a message to me, the host, and I can read it out loud. Oh, here's an early question. There are many challenges in hurricane forecasts. Which one do you think is most challenging and can mostly help improve the forecast in terms of numerical model fundamental theory?
Well, that's a really interesting question, and it's tempting me to go on at length, and I won't do that. I'll say what my top priority is, and it's just the top one. I could give you a whole list. I think we have to move away from this obsession. This is for communication purposes and forecasting, but it also is a technical problem. To move away from this track and intensity dichotomy, I think it's not serving the public at all well. What we need to be doing is moving toward what I call point-wise probabilistic forecasting, so that the interested citizen or business or whatever have you can go in and say, here's my latitude and here's my longitude. What's the probability of winds greater than X in the next 3 days as a function of X? Or what's the probability of being flooded? That's what they really want to know, not where's the storm going to be. But to do that, to give them that probabilistic estimate, we need order 1,000 member ensembles. And I think we can do it. In fact, we are doing it now. I can talk to you offline about that. We're doing it in real time. I can even direct you to a website. I think we have to be moving. To me, that's the most important thing, is to move toward a probabilistic, point-wise probabilistic framework.
Thank you.
I have another.
The machine learning is getting
much attention in
science. What aspects do you think can help in the study of hurricanes?
That's a very good question. I think the machine learning is going to be at least valuable when it is applied to just what I said a minute ago, the estimation of point-wise probabilities given a large ensemble of numerical output. So it's a statistical kind of problem. How do you go from tracks and intensities and rain and so forth from many different ensemble members to probability of conditions at a point? And at the very least, machine learning can help us do that. There are, I'm sure, other applications.
There's a comment from Rammer. I don't know if he's unmuted, but I can read his comment. He says, do you need flawed historical data? The data sets are fine for history. I think you mean that a current method of risk management based on history is flawed.
Well, I sort of mean both. The historical records for some phenomena are flawed. For hurricanes, it's terrible. If you really get down and look at hurricane data, it's not very long and it's very flawed. They weren't never conceived of as a climate data set. Standards changed for measuring wind speed, for converting pressures to winds. It's a mess. Anybody who spent a lot of time with it, it's a mess in the Atlantic. And the rest of the world is really hopeless. It's very bad. In fact, we're doing a bad job measuring hurricane intensity outside the Atlantic, I would argue. So I stick by that. Now, for other quantities like temperature, yes, yeah, they're perfectly good records of things like that.
Thank you. Does
anyone else have any questions?
You could even
chat
if you want to be
unmuted.
Find your name.
Find your name.
Oh, here's one from
Aaron Munsell.
What is contributing to the
forward
shift in latitude at which species are reaching their peak intensity?
Thermodynamic
Changes in windshear patterns, fundamental changes in track.
All of the above. But I think that the dominant thing, Aaron, is that, by the way, hello, it's been a while. The dominant thing, I think, is two thermodynamic effects. One is that for reasons that are kind of interesting, potential intensity is increasing somewhat faster in the subtropics than in the deep tropics. It actually, there's a saturation that occurs for potential intensity if it's being increased by putting greenhouse gases in. If you were increasing it by turning up sunlight, there wouldn't be such a limit, but there is for CO2. The other thing is that as you increase the temperature in the free troposphere, it actually becomes harder to form hurricanes in the first place. So the regions of formation also tend to migrate forward. I think those are the two big reasons, but they're probably not the only reasons.
Dr. Emanuel,
I have two more questions for you.
Do you happen to have a pair of headphones? I'm being told there's a strong echo.
Okay, I do. Hold on just one sec. Me now?
Yep.
Okay.
Can you hear me?
Yes, I can.
Perfect. And the echo's gone. Okay, great. I wasn't sure if that was just on my end. Okay. Another question from Nicholas Reel. Do you expect increased TC-induced precipitation over the ocean as well?
Yes, indeed. I do expect that. And we certainly see that in the synthetic tracks. Without a trim-type satellite up there, I don't know if we'd ever be able to detect it very accurately, but there you go.
Okay, and last question that I have, NASA and NOAA seem to start investing money in small satellites for improving hurricane observation. Do you think small satellites can bring in, refresh things over the traditional big satellites for hurricane forecasts?
Maybe, but I'm putting my money on the first A in NASA, aeronautics. So I'm involved. What I believe what we need to do with tropical cyclones is to monitor them from the stratosphere with drones. And I'm involved in a project headed by a professor at Harvard to build a solar-powered drone, literally powered entirely by sunlight, that flies in the lower stratosphere with an X-band scanning Doppler radar. I'd like to have one of these over each tropical cyclone on the planet. We can do that for somewhat less money even than CubeSats, I believe. So we've got to go back to near field remote and in situ sensing. We can't put all of our money, we shouldn't put all of our money in space.
Great, thank you. Are there any other questions? Okay, none on my end. Thank you so much, Dr. Emanuel, for that talk. It's clear everybody loved it. Thank you. Everybody else, please come back next week as our seminar series continues. Thanks for coming.
Thank you.
Thank you, Dr. Emanuel. That's a great talk.
I'm going to